Imagine our universe, countless eons from now. A cold and empty place. In the emptiness sits a solitary proton, the very last of its kind. This lonely proton has lived a long, long time. This aged universe is now 100 billion trillion years old. And so much has happened over this unimaginable stretch of time. Over all these countless years, the cosmos has constantly morphed and evolved. And this last proton has been witness to it all. If the proton could think, then maybe it would lament all that has passed, as it stares into the endless future of untold years ahead. And like an old man facing his own end of days and his ultimate mortality, it might reminisce a little about times gone by. The story of this proton began 100 billion trillion years before, at a time when the universe was young and hot and exciting. The proton was not born at an exact moment, at a precise time that can be pinpointed. And the story of its birth was, unsurprisingly, a little complicated. So let's go back to its birth. Back as far as our physicists can understand our proton's life with their theories of the cosmos. Pushing back to the ultimate creation of our universe has been the goal of a century of physics. But despite all of the efforts of the smartest minds, so much of these initial moments remains a mystery. So our story begins just after the unknown. Just after the very beginning. 1/100th of a millionth of a billionth of a billionth of a second after the moment of creation. At a time when the universe was nothing but fire and light. It is here that we find the ultimate origin of our proton. Where did we come from? What is our purpose in this immense, unfriendly cosmos? These are some of the deepest questions we ask ourselves as humans. But perhaps the deepest of all is tied to our ultimate origin. Just where did the entire universe come from? The disheartening truth is that the birth of our universe remains unknown. Our physical theories are too incomplete to construct just what happened. But when it was 1/100th of a millionth of a billionth of a billionth of a second old, we think that the universe underwent its first huge upheaval. A burst of cosmic inflation. Quite what drove this burst is as mysterious as the inflation itself. But in just a fraction of an instant, it expanded by more than 1 trillion, trillion, trillion times. In this expansion, the universe was emptied of all that was there before inflation. Then instantly, it came to a shuddering halt and resumed a more sedate expansion. The energy of inflation poured into the universe as matter and radiation. A super dense and super hot soup of the most fundamental of particles. Quarks and electrons smashed together with photons and neutrinos. But the universe continued to expand and cool. Very soon, the universe was 1/millionth of a second old and had cooled to a temperature of a little more than 1 trillion Kelvin. It was finally cool enough for the strong force, one of nature's fundamental forces, to begin to bind the quarks together. And the first components of atomic matter, the protons and neutrons, crystallized out of the soup. The universe was still very hot and very dense. Energetic protons and neutrons collided with electrons and neutrinos. In these collisions, identities flipped as protons became neutrons and neutrons became protons. But the universe continued to expand and cool. By 1 second, and at a temperature of about 1 billion degrees, things began to change. The violence of the collisions steadily diminished. Protons remained protons, neutrons remained neutrons. And the strong force is able to reach out and bind protons and neutrons into the very first atomic nuclei. But the fires of the Big Bang were rapidly going out, and this chemical cooking was soon over. In the space of 10 minutes, this first formation of elements was complete. 75% of the universe remained single protons, the nuclei of future hydrogen atoms. But our proton from the end of time found itself bound with another proton and 2 neutrons. It found itself in the nucleus of the second most common element, helium. Within the nucleus, the strong force fizzed between the protons and neutrons. And 1 trillion trillion times every second, protons morphed into neutrons as neutrons morphed into protons. Their identities now ambiguous. In the first cosmic minutes, our proton was bound into a nucleus where its identity would flip for billions and trillions of years to come. And it would experience so much before it returns to being nothing more than a proton. For many thousands of years, the universe remained a hot plasma, a sea of atomic nuclei and electrons, bathed in high-energy radiation, a leftover from the initial fires. And whilst electrons were drawn to the positively charged atomic nuclei, this radiation continually tore them away. the universe would remain this way for almost 400,000 years, to a time when it had expanded and cooled to only a few thousand Kelvin. The diminishing energy in the radiation became too feeble to tear electrons away, and they finally bound to the nuclei to form the first true atoms. And the universe became neutral. This was a momentous occasion for the cosmos, as it entered its first dark age. In this new epoch, gravity was beginning to work its magic and draw matter together. Locked up in the helium nucleus, the future proton was quite unaware of its coming journey, for the dark age would be only fleeting, and light would soon burst again into the cosmos. At the very dawn of time, other matter was created. Matter that was unlike the protons and electrons in the universe. Except for the action of gravity, this matter was invisible to the fundamental forces, and so it would remain forever dark. The cosmologists just named it dark matter. But the important thing about dark matter is just how much there is in the cosmos. There is 6 times as much dark matter as there is protons and electrons. And so, in the darkness of the early universe, it was dark matter that started to move under the pull of gravity. It began to accumulate into clumps, then clumps gathered into larger clumps, and the gravitational seeds of the future universe were sown. The protons and electrons were caught in the gravitational pull of dark matter, and they too started to pour into the gravitational wells of the dark matter clumps. More and more matter rained in during the darkness after the neutral atoms formed. And these reservoirs of gas grew larger and larger. Somewhere in this melee was a single helium atom, home to our future proton. Unlike dark matter, however, the atoms of gas can interact through electromagnetism, meaning it could radiate energy and cool. It could collide and collapse, shrinking to ever smaller knots of high density within the halo of dark matter. Eventually, a critical point was reached and the universe changed again. Some of these knots were more massive than thousands of our Sun. Their densities and temperatures soared. Collisions between atoms became more violent, with electrons ripped back off nuclei. But it was in the core of this soon-to-be star that conditions became extreme. Eventually, a point was reached where the core was many millions of degrees Kelvin, and the collisions between the raw protons at atomic nuclei became more violent. Conditions were similar to the elemental cauldron of the Big Bang. And nucleosynthesis, the creation of heavier elements, began again. This nuclear fire released immense amounts of energy that flowed from the core and towards the surface, until it finally burst through and flowed out into space. The The universe was now 100 million years old, and the first stars began to shine in the heavens. Let there be light. Being massive, the nuclear reactors at the hearts of the stars burned ferociously. And these stars glowed brightly in the ultraviolet and at higher energies. This radiation filled the cosmos, smashing into neutral atoms deep in space, again tearing away electrons. Once more, the universe was ionized. Our helium atom found itself in the atmosphere of one of these giant stars. Ionized, with no electrons, but far from the elemental alchemy taking place in the core. It was buffeted by the flow of energy radiating outwards and was caught in immense currents of convection. But it retained its identity as it swirled through the stellar layers. However, this time was destined to come to an end in little over a few million years, as eventually the nuclear reactor at the stellar heart must run out of fuel. At the start, it steadily transmuted hydrogen into helium in its core, providing the energy to sustain the star for most of its life. Eventually, the hydrogen fuel in the core is exhausted and the nuclear power starts to dip. The immense gravity begins to bear down on the core, driving temperatures higher. In this extreme case, now the helium, which was simply a waste product from the burning of the hydrogen, becomes new fuel. Within the ultra-dense core, helium is burnt to produce carbon, giving the star a new lease on life. But now the nuclear reactor is burning hotter and faster. The energy production can only continue for 1/10 of the life of the star before it's exhausted. And before too long, the helium fuel has gone and it's carbon's turn for the furnace. Gravity bears down and a new nuclear cycle, carbon to oxygen, is ignited. The star, however, is racing to its demise, as carbon burning will last only a few hundred years. After this, the oxygen is burnt into silicon, the fires taking only 6 months to exhaust the fuel. As silicon starts to burn into iron, it has reached the end of its journey. Silicon burning is ferocious, and within 1 day, the fuel is gone. At the end, the core of the star is a ball of super hot, super dense iron. This is bad news, as iron is the most stable of the atomic nuclei, and so it has no energy to liberate in nuclear reactions. In an instant, the nuclear fires go out, and the outward push of radiation ceases. There is nothing to prevent gravity's inexorable pull, and the atmosphere of the star crashes downward. As these outer layers smash into the core, the extra energy transmutes iron into heavier elements. And vast quantities of energy are instantly released in this burst of nuclear burning. The new outward rush of energy reverses the collapse. The collapse has become an explosion, and the star tears itself apart. Such dazzling displays, supernovae, fizzing through this first generation of stars. Whilst the core of the star might have been crushed out of existence, pummeled into the point-like singularity which sits at the heart of a black hole, our helium nucleus is thrown unharmed into interstellar space. But its journey is far from over. For a while, the nucleus may wander into stellar space, before eventually finding itself drawn into an immense cloud of gas. This cloud is similar to the one it found itself in before the light of the first stars. But now it is polluted with a sprinkle of heavy elements from the exploding supernovae. The cycle of stellar life began again, with these gas clouds cooling and fragmenting. Chunks of gas begin to collapse as the next generation of stars begin to form. Once again, our atom of helium was caught up in the maelstrom, falling into the embryonic stars, now caught deep within the stellar core, and witness to the birth of a new star. As temperatures soared, the nuclear reactions rumbled into life. Again, hydrogen fused into helium, and the temperature continued to climb higher and higher. At almost 200 million degrees, helium began to burn into carbon and oxygen. And this was the fate of our helium atom, now transformed into carbon within the stellar core. This new star was a little more massive than our own Sun, burning more slowly through its nuclear reserves, shining for several billion years as it relied on the burning of hydrogen as its source of energy. But the star changed as it transitioned to burning helium once its hydrogen fuel was depleted. And it was this change that signaled that its end was coming. Instead of burning steadily, the output from the nuclear core came in bursts, and the atmosphere of the star began to pulse, grow, and shrink with the changing energy flow. The carbon atom containing our future proton had been carried from the core and embedded in the pulses. As eventually, the pulse became so violent that the atmosphere was ejected from the star. Inside this expanding shell of gas, the stellar core remained, a super-dense white dwarf, a dead star heart of carbon and oxygen. Now it was hot, energized with the residual heat from the nuclear fires. But over billions of years, it was destined to cool to the frigid temperatures of space. The carbon found itself floating amongst the stars, spending eons just wandering. Eventually, it found its way into another gas cloud, heading again for life in a star. Once more, the gas began to cool and fragment. Pieces began to collapse into baby stars. And the carbon atom was going along for the ride. If the carbon atom could think, "Here I go again," would have undoubtedly crossed its mind. But as this new star began to assemble, the carbon was not in the stellar core or atmosphere. It was much further out, orbiting in a thick disk of material around the star. Perhaps it might have thought, "This time, things are going to be different." The universe was now 8 billion years old. Several generations of stars had risen and fallen. And this newest star found itself with more than 100 billion others. All these stars orbiting together in a galaxy we call the Milky Way. Our cosmic home, the Milky Way galaxy, began to form when the universe was a few billion years old, with its stars blooming at the heart of its own dark matter halo. And over the billions of years, it had continued to draw in stars and gas. And in its immense clouds of gas, new stars continued to form. Now 5 billion years into the life of the Milky Way, this new star shone with brilliant white light. For this star is our Sun. And as its own nuclear reactions were commencing, its orbiting disk was beginning to coagulate. Lumps of matter became the seeds of future planets, growing through the accretion of more lumps. And it is through this that the destiny of our carbon atom was set. The planets grew quickly, and the carbon atom found itself in the crust of the third from the Sun. The surface remained molten as more rocks rained down, but eventually this stopped. The cooling crust solidified, and icy comets flooded the surface with water. When the universe was 9 billion years old, the Earth was born. The environment within the planet was very different to that inside the star. Instead of electrons being ripped apart by searing heat, the carbon joined with other atoms, interlocking into complex molecular combinations, taking part in chemical reactions, and in no time at all, these reactions changed the face of the planet. Through chemical steps that we currently don't understand, life on Earth began soon after it cooled and water flowed on the surface. But atoms of hydrogen, carbon, oxygen, and iron drove the molecular machinery, and simple life flooded the planet. Life stayed in simple form as single cells for billions of years, and our particular carbon atom was weathered into the seas. It was when the universe was 13 billion years old that more complex life appeared. And a few 100 million years until the first plants inhabited the land. The carbon atom now found itself part of this life, absorbed into the structure of a strange but lush plant on the edge of a warm sea. In the water, jellyfish pulsed and primitive fish swam. Insects flew amongst the plant fronds as they waved in the breeze. As the first animals were taking their initial steps on land. Of course, the carbon knew nothing about life as it jostled with other nearby atoms. And in the blink of a cosmic eye, the plant has died and become buried underground. As time went on, the pressures increased and materials transformed into rock. Within the rock, carbon atoms were squeezed closer and closer together. Here and there, they locked into a crystal of diamond, tightly bound deep beneath the earth. Most diamonds remain hidden forever, deep within the crust. But when the universe was almost 14 billion years old, some life was hunting for them. It was now that humans walked upon the earth, and humans have an eye for shiny things. As they dug into the earth, hunting for gold and silver and precious stones, our diamond was ripped from the rocks and briefly adorned some beautiful people. But very soon it was back in the ground and lost to the rocks. Hidden again, it missed the monumental changes that then tore across the sky. As the Andromeda Galaxy, an almost twin of the Milky Way, slammed into our own. This gravitational tug-of-war ripped both of these giant galaxies apart. But deep in the Earth, our proton was blind to this excitement. During this titanic collision, immense gas clouds smashed into each other. Fragmenting and collapsing, these clouds were churned into a burst of stellar birth. For a few million years, the heavens burned with the light of these newly formed stars. Bursting with supernovae, this cosmic firework display was stunning. Some of the gas was funneled down into the hearts of the colliding galaxies, providing food for the monsters that lurked there. Drawn in by the intense gravitational pull of supermassive black holes, this gas swirled down to its ultimate doom. Sitting at the heart of galaxies, these supermassive black holes are immense gravitational beasts. Millions and billions of times the mass of our Sun. Today, the Milky Way's black hole is about 4 million solar masses. But over time, it will continue to grow, feeding on that which strays too close. Streams of gas jostled on their way into the black holes. And in the crush, the gas was heated, superheated to millions of degrees. As it swirled deeper and deeper, the hotter it got, and the extreme energies started to glow, with light and more intense radiation. The black holes glowed brightly, brighter than anything else on the sky, as gravity drew the remains of the collision back together. But in another cosmic blink, all this excitement was over. As the black hole finished its meal, and the formation of new stars steadily died away, But the proton, hidden in the darkness, missed all of it. Deep within the Earth it remained for 5 billion years, heaved through the rocks and weathered to the surface. When it next saw the light of the sun, the humans were gone and other life thrived. Maybe this new life also coveted shiny things, maybe not. But soon enough, the diamond was lost again underground. And around and around and around it went. Eventually, when the universe was 19 billion years old, the sun was finally facing its end of days. With its hydrogen exhausted, the internal structure of the sun will shift and change, and begin to feed instead on helium. But this internal rearrangement will upset the nuclear balance, and the sun will begin to expand and grow. Firstly, its swollen body reached out and engulfed the innermost planet, Mercury. Then it grew and grew, swallowing Venus, which disintegrated as it fell towards the stellar core. Earth's time was running out. The broiling atmosphere of the sun finally reached the Earth's orbit. The roar of the sun's outer layers boiled off the oceans and scoured away the atmosphere. The Earth began to disintegrate, material torn from the surface by the scrub of the sun, steadily dragging on the Earth's orbit and pulling it towards the core. The diamond was lucky, ripped from the Earth and flung into the sun's expanding atmosphere. The pulverized planetary rock dispersed into the wash of hydrogen and helium as the last remnants of planet Earth spiraled into the unbearable lightness of the burning star. The sun was rapidly approaching the very end of its life. The pulses through the sun's atmosphere steadily grew in intensity, and the nuclear reaction within its core became more and more unstable. With one final immense pulse, the entire atmosphere of the sun was detached. Launched into space, this stellar material is destined to mingle with others amongst the stars. The diamond was part of the debris that was rocketed out into space. Part of the smashed planetary rocks and atoms flung back amongst the stars. Most of the Earth now lies within the leftover nuclear core, which sits at the center of the expanding atmosphere. An extremely hot and dense star known as a white dwarf. White dwarfs are extreme objects, with much of the mass of the sun packed into 10,000 kilometers. No nuclear fires burn within their hearts, and they are supported by the quantum pressure of electrons. But these stellar remnants are dead, destined to sit and cool to the blackness of space. And their atoms will not take part in the continued life cycles of stars. This story of stellar birth, life, and death continued. Atoms continually recycled into stars, and the diamond was dismantled back into individual carbon atoms on its first return to a star. Each time back was similar, but sometimes in the core, sometimes the atmosphere, sometimes a planet. With countless eons spent wandering interstellar space in between. But there was a shift across the universe. Something that changed everything. The young universe had been vigorous and active, sparking with stars formed from collapsing gas clouds. Many stars were born in the violent collisions that marked the evolution of galaxies. And over the billions of years of the life of the universe, many stars died. Massive stars die first, tearing through nuclear fuel and exploding as supernovae in millions of years. Stars like the Sun last longer, burning their fuel over billions of years before reaching their demise. Whilst their stellar deaths replenish interstellar clouds with raw material for the next generation, each leaves behind a dying remnant, a black hole, white dwarf, or neutron star. With each cycle of star formation, less and less material is available for the next generation. And like many who have reached middle age, the universe has calmed as it's gotten older. Less galactic collisions, coupled with dwindling nuclear fuel, means that star formation is dying. And we are in the twilight of the time when stars burnt across the heavens. When the universe was 14 billion years old, and humans walked on the long-forgotten Earth, already more than 95% of all the stars that would ever live had been born. And many of those had already died by this time, leaving the myriad of dead stellar hearts behind. The universe was hurtling towards darkness. And things were destined to get a whole lot darker, reshaping in a way that would change it forever. The transition had started long ago, caused by a mystery that had remained hidden. A mystery that cosmologists now unimaginatively call dark energy. And it will eventually drive the universe into never-ending darkness. At the close of the 20th century, astronomers made a startling and disquieting discovery. The expansion of the universe that had continued since the Big Bang was accelerating. Their cosmological theories had predicted that the expansion should be slowing, slowed by the gravitational drag provided by the presence of matter. They thought they must have made a mistake, and checked again. But they could find no error in their approach or mathematics. Eventually, they had to face the fact that it looked like they were correct. And they announced to the world that the universe was stranger than anyone imagined. But the discovery of the accelerated expansion was just the start of the problems for the universe. What was causing the accelerated expansion proved to be the real conundrum. Their equation told them the source must be a cosmic field of energy. A mysterious energy that was like no other across the universe. and this dark energy would come to dominate the cosmic evolution. In the early universe, dark energy was present but played no role in shaping the cosmos. It was massively outweighed by the presence of matter and radiation. It was these two that dictated cosmic expansion in the formative years of the early universe. But whilst dark energy was hidden, all it had to do was wait and bide its time. As the universe expanded, matter and radiation thinned out, and their densities steadily dropped. Very quickly, radiation lost its dominance, and expansion was dictated by the presence of matter. But dark energy remained in the background, waiting. As one day, in the struggle for cosmic dominance, it was bound to win. One of the strangest properties of dark energy is that it is oblivious to expansion, its density remaining constant as the rest of the cosmos diminished. But matter continued to thin out as the cosmos aged, until, when the universe was 8 billion years old, dark energy finally took over. Through this dark energy domination, cosmic deceleration turned into cosmic acceleration, and matter continued to thin out, becoming less and less dense as the years ticked by. Today, 14 billion years after the Big Bang, the energy density of dark energy is more than twice that of matter. And into the future, dark energy's dominance will continue to grow. 100 billion years from now, the accelerated expansion will irreparably change the heavens, as it will drive galaxies over what's known as the cosmic horizon. This means that light emitted from cosmological sources will eventually never reach us, as this light will lose its battle with the ever-increasing distance as it tries to race towards us. For any observers in this future universe, the sky will steadily appear to grind to a halt. And then these distant galaxies will fade from view. Beyond the stars in our galaxy, the night sky will be painted an inky blackness, the darkest of the dark. And it will appear that the universe is composed of nothing but our aging galaxy, embedded in the void. Within the Milky Way, stars continue their lives, and gas will continue to cycle in and out of stars. Each generation of stars pollutes the interstellar gas with more and more heavy elements. But with each generation, more matter gets locked up in the dead remnants of the stars. In dense stellar hearts, like white dwarfs, or locked into extreme gravitational prisons of black holes. Over 50 trillion years, our future proton also ended up getting locked into heavier elements, eventually finding itself in the nucleus of iron, the most stable of nuclei. It continued its cycling through generations of stars, but now could not contribute to energy production. But it was lucky enough to be ejected into space time and time again, and not locked away in a stellar remnant. When the universe was 85 trillion years old, the iron found itself in a newly formed star. But this is the last time this atom would take this particular journey. For this star was a tiny red dwarf, only a tenth of the mass of our Sun, and one of the last to be born, formed from the dwindling supply of fuel remaining between the stars. Small stars live the opposite lives to massive stars. The opposite of live fast, die young. Their nuclear fires run much cooler and burn through their nuclear fuel much more slowly. They glow dimly, but that glow will shine for many tens of trillions of years, far longer than the mere billions of years of our Sun's life. So our proton, locked in iron and jostled by the warm nuclear fires, settled in for the first part of cosmic eternity. Across the Milky Way, stars continued to die, and new stars were no longer born. Now and again, a gigantic star would end its life in a massive explosion, briefly lighting up the cosmos. But the more numerous red dwarfs end their lives quietly, simply slipping into the darkness. As each was extinguished, the darkness grew across the galaxy, and light faded across the cosmos. After 100 trillion years, only the glow from the decreasing number of red dwarf stars remain. Their dull red glow, not enough to illuminate the myriad of dead star hearts in the remnants of the Milky Way. One by one, the red dwarfs continue to go out, as the ultimate darkness creeps closer and closer, until finally, when the universe is more than 100 trillion years old, the very last red dwarf remains. Deep within this final star, the nucleus of iron still sailed back and forth in the atmospheric currents. In the relative coolness, it had managed to gather some electrons and was once again atomic. But the good times could not continue forever, as the final nuclear fuel was burnt, and finally, the light from the last star went out, and utter darkness was across the deep. As it cooled, the last red dwarf joined the countless other dead stellar hearts, all held bound together by their combined action of gravity in the dying Milky Way. Every so often, a gravitational tussle slingshots one of the remnants out at tremendous speeds, breaking its bond with the Milky Way and destined to wander in the emptiness of space. It seems again that the story of our proton is now over. For what could be left? It is bound within a nucleus of iron, buried deep within a dead star as the universe continues to age. over the countless years to come, the star will continue to fade into complete blackness. And as it does, it cools towards a temperature of absolute zero. However, the universe is still not done, and there are more changes to come. Even in the darkness and over many years, the cosmos will steadily transform again. In this darkness, matter itself will begin to melt. And after the unimaginable number of years ahead, the dead stars will dissolve into nothing. Does anything feel more stable than the stability of matter? You know that the world of tomorrow will be very much like the world today, as the material of you, your house, and the world around you will just be there. And the built-to-last structures of the Egyptians, Greeks, and Romans show this over thousands of years. Except we know that some matter is not truly stable. The discovery by Henry Becquerel and the Curies at the end of the 19th century showed this. That some elements could be transmuted into others through the emission of strange radiation. This radioactivity showed that something was threatening the stability in the very hearts of atoms. Physicists have now discovered the source of this atomic instability, finding quantum fuzziness and probability within the atomic nucleus being responsible for the transmutation. But radioactivity appears to be relatively rare, appearing in certain isotopes of certain elements. And it doesn't appear that radioactivity is a threat to our stability of matter. Quantum mechanics, however, is a patient beast with time on its side. Tiny probabilities are bound to become realities if we wait long enough. What does this mean if we look out into the drawn-out destiny of the cosmos? Is the apparent stability of matter nothing but an illusion as the universe creeps into darkness? We are now millions and trillions of years into the future of our universe, sitting in the ultimate blackness. No light will shine in the relic of our galaxy. And in the darkness, many billions of dead stars will continue to roam, a distant memory of the time when light shone in the sky. Ever so rarely, the gravitational wanderings of the dead stars will bring some of them together. And in this merry dance, some stars will be accelerated to tremendous speeds, ejecting them out into the ultimate void, lost forever into the cosmos. And with each ejection, the Milky Way, robbed of some energy, will contract. Time and time again, black stars are ejected. Time and time again, the remainder shrinks even further. This brings the stars closer and closer to the dark heart of the Milky Way, where lies the gravitational monster, the supermassive black hole, Sagittarius A star. In the future universe, through the continued galactic contraction, the dead stars are brought closer to oblivion. Closer and closer to the gravitational clutches of the central black hole. And one by one, each star will be drawn in and captured, with one final burst of light as they are torn apart and consumed. Over the eons of time, the Milky Way will completely evaporate, with the dead stars either flung out or being eaten by the black hole at its heart. Our future proton again was lucky, as its black star was ejected into the endless night, and in our ever-expanding universe, remained utterly alone. The wandering through nothingness continues, eon after eon. The black star is frigid, as cold as space itself. In our understanding of these future times, speculation grows in what we know in our scientific theories, growing the further we look into the future. But if nothing changes, over time, matter itself is destined to melt. When the universe reaches the grand old age of 1 trillion years, due to the ever-increasing expansion, its temperature will hover just above absolute zero. Over such immense timescales, even rare occurrences come to dominate, and the stability of matter will be seen to be nothing but an illusion. Even in the frozen star, atoms still jiggle with a whisper of quantum energy. And rarely, oh so rarely, a jiggle will dislodge an electron and send it skyward. Most are attracted back, but some will escape the gravitational pull of the star. These electrons, carried by the drag of expanding space, are forever lost in the endless void. The process continues as more and more material is lost into darkness. Electrons are ejected. Atomic nuclei are broken down. The star evaporates, finally ground back into fundamental particles, lost in the expansion of the aging universe. The breakdown of atomic matter into its constituent pieces returns our proton to the universe. As the star melted, the iron atom steadily lost its electrons. Then the nucleus itself started to disintegrate into its constituent parts. Protons and neutrons steadily went their own ways. And our proton, still a proton, was itself again. The matter from the rest of the star quickly vanished into the nothingness. The expansion of space, driven by dark energy, still forced the density of matter lower and lower. And the proton quickly found itself alone. Other than a rare photon or electron, there was nothing but space. The universe was steadily winding down, coming to a halt as it ran out of energy. Once again, we have found ourselves at the end of our story, in a cold and empty universe. But as we've seen, the cosmos always seems to have tricks to play, and the ability to change and evolve. Our proton will have to wait until the edge of eternity before it faces the end of time. And that wait will be a long one. We are now truly approaching the end of our story. The universe is now 1 trillion years old. And in the cold and in the dark, there sits a lonely proton. It has lived a long time and is the very last of its kind. There once were so many protons, the final debris from the stars that shone so long ago. But while they seemed impervious to aging, physics had one last trick up its sleeve. For hidden deep in the equations is the possibility that protons are not truly eternal. And after so many years, they too decay. Physicists are still trying to determine the mechanism of proton decay. But it's clear that in an instant, a proton would disintegrate into electrons and photons. In this distant future universe, all of the protons have undergone this ultimate demise. And for our final proton, its time has come. This proton that had been forged in the first instances of the universe was nearing its end. It had been witness to the birth of stars, to the end of stars. It has played its role in the universe, in the lives of stars, and the phenomenon of life itself. But it had seen so much more across the endless eons when the stars went out. After all this time, it took just an instant, and it was all over. In a tiny flash, the proton was no more, ground down into simpler particles. Protons might be extinct, but the universe will still go on, maybe forever and ever. What awaits in the infinite time ahead? The cosmos may continue to age, continue to expand, continue to cool. An ever-thinning soup of nothing but scattered fundamental particles. But the universe is not over yet, for in the darkness, lonely giants roam. And it's the death of these giants that will result in the last bursts of energy in the cosmos. Scattered through the cosmic immensity are black holes. Black holes that had been immune to the disintegration of matter. Some are as massive as our sun. Others are billions of times larger. But even black holes will not last forever. The eventual demise of black holes will be because of Hawking radiation. The slow leak of energy from the hole due to the action of quantum mechanics in its outskirts. Particles and photons are conjured from the quantum vacuum due to the presence of the event horizon. The one-way barrier surrounding a black hole. A barrier where once you fall in, you're never coming back. This radiation, flowing into the darkness surrounding the black hole, carries away energy. And this energy is tapped from the source of the black hole. The mass sitting at the central singularity. The mass of the black hole is gently whittled away due to the Hawking radiation. And eventually, if it can swallow no more to replenish it, the mass of the black hole will evaporate away. The evaporation of black holes begins slowly, an imperceptible dribble of energy. But steadily the mass of the black hole is transformed and lost into the cosmos. As it shrinks, the rate of energy loss increases more and more. And in its final moments, the black hole vanishes in an immense burst of light. The smaller black holes will be the first to go, with sporadic flashes in the darkness. More time is needed for more massive black holes to reach this point of ultimate destruction. And for the true monsters, billions of times the mass of the Sun, unimaginable times are needed. But after a Google of years, that is one followed by 100 zeros, the last will be gone in a blaze of glory. With the black holes gone, the universe's true journey into eternity begins. The expansion continues, and energy dwindles away into the vacuum. The cosmos is winding down to a state where nothing can happen. The universe is approaching a state known as maximum entropy. A maximum entropy universe is a strange place, where even time itself is hard to define. For how can there be time if nothing ever changes? And if nothing changes, it seems that we really have reached the end of our story. But there is one potential savior that might rewrite the ultimate future, and that is dark energy. Through the history of the universe, dark energy has been there. It firstly sat in the background, having no influence. But over time, its influence grew. It dominates the universe today, and this domination will continue into the infinite future. And it will be there when the disorder of the cosmos rises to its maximum. Today, physicists struggle to understand the true nature of dark energy. Just what it is and how it behaves essentially remains an utter mystery. But they know that it is a field of energy of some sort spread throughout the universe. And like all energy, dark energy should be subject to the rules of quantum mechanics. Some physicists wonder if dark energy can decay. Quantum tunneling from a higher energy level to a lower one. Whilst the universe would have to wait a long time, more than 10 to the 10 to the 10 to the 50 years, this release of energy will spell the end of our universe, and possibly the birth of another. In a burst of energy, our universe will be gone, completely erased in less than a moment. There will be a new bout of accelerated expansion in which new universes will be forged. In this broiling mess of space and time, even the laws of physics may be rewritten, and a sea of new and strange universes may be created. The death of our cosmos could give birth to a host of daughter universes, some resembling their parents. Their initial moments would be fiery and hot, with searing energy transformed into matter as they cooled. Quarks would emerge from the soup and would begin to gather a millionth of a second after cosmic birth. And this new universe would be filled with newly formed protons and neutrons. Maybe, just maybe, this cycle of cosmic life will begin again.